Today we're going to talk about some applications of differential equations. So solving differential equations in the context of population change and temperature change and other things like that. First, we're going to look at a topic that you may have covered in your science classes, which is Newton's law of cooling. What that really means in a nutshell is that, say you have a bowl of hot soup in a room temperature room. What's going to happen, what Isaac Newton figured out, is that the soup cools quickly at first, and then it starts cooling less and less quickly as it approaches the temperature of the room. So when the temperature difference is big, it cools fast. When the temperature difference is little, it cools more slowly. That's a pretty intuitive thing to understand, and so it actually makes it pretty easy to write a differential equation. So let's look at this example. Miss Allen brings hot coffee into room 205. When she enters the room, her coffee is 150 degrees Fahrenheit. The temperature in the room is 70 degrees Fahrenheit. The rate of change of the coffee's temperature is directly proportional to the difference between the coffee temperature and the room temperature. And so our goal is going to be to write a differential equation that models this situation. Let's start with this mathematical term. The rate of change of the coffee's temperature. So we can call the coffee's temperature, let's call it F for degrees Fahrenheit. So the rate of change of the coffee's temperature, so change in temperature over change in time, is, so we're going to put an equal sign, directly proportional, remember that's some proportionality constant K, to the difference between the coffee temperature and the room temperature. So we need to write the difference between the coffee temperature, which changes, so we'll call it F, and the room temperature, which is a constant 70 degrees Fahrenheit. So this is a differential equation that models the situation. The proportionality constant K can be determined experimentally, but I'm going to give it to you for this problem. We're going to be given that K equals negative 0.05. We see that it's negative because the coffee is cooling. So dF dt equals K times F minus 70. Also, we do have an initial condition. F of 0, the coffee temperature times 0 is 150 degrees Fahrenheit. So here's our differential equation that models this situation. Here it is written out again. What I want to do first is use Euler's method with delta T equals 1 to approximate the temperature of Miss Allen's coffee after 4 minutes. Hopefully you remember from when you taught yourselves this last Friday that Euler's method is the idea of using little tiny tangent lines to build from one point to another point on a function. The easiest way for me to organize Euler's method is to set up a chart. I guess I'm not using x and y. Instead of x, I'm using t, and instead of y, I'm using x. And here, to find my next point, I'm going to use the formula dF dt, so my slope, times my change in time, plus my original. That'll get me my new F value. So I start with the initial condition 0, 150. And I'm trying to figure out the temperature at 4 minutes using a step size of 1. So I'm going to do a step size of 1 to get to 1, then 2, then 3, and then 4. We extend those lines. To find my next temperature value at time 1, I can approximate it by using my slope, negative 0.05, f minus 70, f is 150, times my step size of 1, plus my original value. And using a calculator, I can see that that is 146. That makes sense. It dropped about 4 degrees Fahrenheit in the first minute. To find my F value after 2 minutes, I can use the same formula, my slope, except this time my temperature is 146 minus 70 times the step size of 1 plus 146. And using a calculator, I get 142.2. I can do it again. 142.2 minus 70 times the step size of 1 plus 142.2. And I get 138.59. And if I do it one more time, I get 135.161. And so using Euler's method, I have shown that my coffee temperature after 4 minutes is approximately 135.161 degrees Fahrenheit. I want to know exactly when my coffee reaches 90 degrees Fahrenheit. Because once it reaches 90, I don't really like drinking it anymore. But I don't want to just approximate this like I did with Euler's method. I want to actually solve it. So what we're going to try to do is let's solve this differential equation analytically like we did yesterday. And to do that, I'm going to use separation of variables. So I have my differential equation. df dt is negative 0.05 times f minus 70. And I actually want to find my original function, f. To do that, I'm going to separate my variables. So I'm going to move the f minus 70 over to be with the df dt and leave the negative 0.05 on the other side. Now that I've separated my variables, I can integrate both sides with respect to t, but really that's integrating the left side with respect to f. It's equivalent. Then I can anti-differentiate, get natural log of the absolute value of f minus 70 equals negative 0.05 t plus some constant. I want to solve for f, so I'm going to exponentiate both sides. Again, I'm going to skip some steps with my constants, and if you need help with that, I would look back at the video from yesterday. That's going to become a big constant out front times e to the negative 0.05t. And then I can solve for f by adding 70 to the other side. I'm not done yet because I can use my initial condition to solve for C. So I know that my temperature is 150 when T is 0. So C e to the 0 plus 70. E to the 0 is 1. So C just equals 80. Meaning my complete function is 80 e to the negative 0.05 t plus 70. I actually want to use this model. Let's figure out what my coffee temperature is after 4 minutes, because that's the problem that I tried to answer with Euler's method. If I plug in 4, I get 80 e to the negative 0.05 times 4 plus 70. Take a second and do that on your calculator. I get approximately 135.498 degrees Fahrenheit, which compared to when I use Euler's method, is only about 0.3 off. So that's pretty good. Euler's method did a pretty good job approximating that. So that's just an interesting note. But what I really want to know is how long until the coffee reaches 90 degrees Fahrenheit, which is when I don't want to drink it anymore. What I can do is take my original equation, set it equal to 90, and solve for t. This is going back to solving exponential equations. So we can subtract 70. Then we can divide both sides by 80. We can take the natural log of both sides. Natural log and the e are going to undo each other. And then divide both sides by negative 0.05. So that's the exact answer. And you can use a calculator to see that I have approximately 27.726 minutes before my coffee becomes too cold for me to drink. I know that was a lot of steps, but I hope you see that it's exactly what we did yesterday, just in a context, separating those variables. Let's do another example, this time a population example. So our situation is that Phil is raising polar bears in his backyard. The rate of change of the number of polar bears, which we'll call P of T, in his backyard is directly proportional to the quantity 400 minus P of T, where T is in years. When T equals 0, so right now, the population is 20, and 3 years from now, the population is 90. And I want to find the population when T equals 5. Our first step is going to be setting up a differential equation that models this situation. So it says the rate of change of the number of polar bears in his backyard. So change in polar bears, which we call P, over change in time, is directly proportional to the quantity 400 minus P. So here's our differential equation that models the situation. We're going to try to find the actual population function. And to do that, we're going to solve this differential equation by separating variables. So let's start. We are going to multiply both sides by 1 over 400 minus p. And we'll still have a k on that side. And then we're going to integrate both sides. It's really easy to anti-differentiate the right side. We just get kt plus some constant. On the left side, I want you to be really careful. This is super, super important. We can see that it's going to be natural log of the absolute value of 400 minus p. But if you were doing u sub, notice that your u would be 400 minus p. Your du would be -1. So we do need to multiply by a negative to counteract that inner function of 400 minus p. This is so important, this negative right here. I will tell you that that is on your quiz next week, and a lot of students forget that negative. Now we want to keep solving for p. Before I can exponentiate both sides, I do have to get rid of the negative. So I'm going to divide both sides by -1. Get negative kt minus c1. Then I'm going to exponentiate both sides. I'm going to get 400 minus p, and I'm going to skip some steps and let myself get a big constant out front, e to the negative kt. And then I'm going to solve for p and get p equals 400 minus ce to the negative kt. I can use my initial population of, what was it, 20 to solve for c. So I'm going to let population is 20 when t is 0. So I know that's going to be e to the 0 and just be 1. So that tells me c equals 380, meaning my function is p of t equals 400 minus 380 e to the negative kt. The difference here is that we were not given k. However, we were given another data point, and that is that at time 3, the population is 90. So I know that p of 3 equals 90, which equals 400 minus 380 e to the negative 3k, if I plug in 3 for that t. And what we can do is solve for k using our techniques for solving exponential equations. So I'm going to subtract 400 and get negative 310 with negative 380 e to the negative 3k. Then I'm going to divide by negative 380, get 31 over 38 plus e to the negative 3k. I'm going to take the natural log of both sides. Get natural log of 31 over 38 equals negative 3k. And so K is going to equal natural log of 31 over 38 divided by -3, which using a calculator is about 0.68. That was a lot of work, but now we have our model for the number of polar bears in Phil's yard at any time t. So let's write that out. We have population as a function of time is 400 minus 380 times e to the negative point. Oh, I need 0.068, my mistake. And there's our model. Now we can answer the question that we started with. What's the population after 5 years? We can plug in 5, and using our calculator, see that there are about 129 527 polar bears in Phil's yard after 5 years. There is one more thing that I want to talk about with this, which we're going to get into more fully in a little bit. I want to know, when does dp/dt equal 0? And think about it, what that means, when is the rate of change 0? When is the population not growing? And if you go back to that differential equation that we wrote, we can see that dp/dt is going to equal 0 when p is 400. So dp/dt equals 0 when p equals 400. What that means is that the population is going to stop growing when p equals 400. We call this the carrying capacity. When there are 400 polar bears in Phil's backyard, the population is going to stop growing. Another way we can write that is that the limit as t goes to infinity of our function 400 minus 380 e to the negative 0.068t equals 400. As time goes to infinity, that population is going to approach 400. Phil can only fit 400 polar bears in his backyard. I want you to try finding the model for this population. I want you to solve this differential equation and find a population model, and we're going to talk about it. If you'll pause this video now, try this one on your own. And when you unpause, you can watch me do the solution and check your work. Okay, so to solve this differential equation, I'm going to multiply both sides by 1 over p. I'm going to integrate. Get natural log of the absolute value of p is 0.4 t plus some constant, which I know if I exponentiate solve for p, I get some big constant, c e to the 0.4 t. I'm going to plug in my initial condition 0, 100 and get 100 equals c e to the 0, which is 1, which means that my final population model is 100 e to the 0.4 4t. So that should be your final answer. This is just an exponential function. So actually what this looks like, if we were to graph this, we know that we have some starting value of 100, and it grows exponentially. If you look at this model, when does dp dt equal 0? Well, it only equals 0 when p is 0. So here we only don't grow when we have nothing in our population. But there's no carrying capacity. It just keeps on growing forever and ever and ever. That is a decent population model if you have unlimited space. But a lot of times we do have constraints on our populations, like land and resources. And so what I want you to try next is a population that does have a carrying capacity. And you can see here that the carrying capacity is 500. If P is 500, dP dt equals 0 and our population stops growing. So I want you to try this one on your own. You will have a question that looks exactly like this on your quiz. So take it seriously. I want you to pause the video now, try this one on your own, and then you can check your work. So again, I'm going to separate my variables. I'm going to integrate. Remember that I get a negative natural log because of the inner function of 500 minus p. What I have to do first is get rid of that negative. So I'm going to divide both sides by -1. And then I'm going to exponentiate. I'm going to skip some steps and just get a big constant up front. And then my population model is 500 minus c, the -0.4t. I can use my initial condition of 0, 100. E to 0 is just 1. And so I know that c equals 400. And my final population model then is 500 minus 400 e to the -0.4t. If you were to graph this function on your calculator, you'd see that it looks, we still have that initial condition of 100, but it looks something like this. It levels out as you approach 500 because the population stops growing. It can't get above 500 because that is the carrying capacity. Which leads us to our most robust population model, which is a logistic differential equation. You've probably talked about this curve in a science class. But most population models are best described by a logistic differential equation, which looks something like this, what we call an S curve. If you see dP dt equals kp times 1 minus p over n. That's actually a really difficult differential equation to solve analytically because we have two p's here, and so separating the variables gets a little bit complicated. But there are a few things that I want you to note about this model. First of all, you have your carrying capacity when P equals N, because that's where dp dt equals 0. Also note that dp dt equals 0 when P equals 0 from this first term right here. And so we have an asymptote there as well. You can't grow if you have no population. You can't grow when you reach your carrying capacity. Another thing that you should know is that a lot of times the AP exam will give you this, and they'll ask you, when is the population growing most rapidly?
Kelly, can you come to the front office, please? Kelly, can you come to the front office?
Sorry about that. It'll ask, when is the population growing most rapidly? And you can see that it happens right there at the inflection point of the logistic curve. At this inflection point, that's when our slope is the steepest. When we're far away from our carrying capacity, we grow faster and faster. But then when we get closer to our carrying capacity, we grow slower and slower. And so you can algebraically prove this, but it is a fact that I'm just going to give to you. This happens when the population is halfway to the carrying capacity. That's when your population is growing the most rapidly. So for example, say that I give you the logistic curve that models the population of polar bears. dp dt equals 0.5p times 1 minus p over 20. Two questions that the AP exam could ask you about this population when you wouldn't even have to solve anything. One of those is, what's the limit as t goes to infinity of your population? The good news is that you don't have to do any math for this. This is just another way of asking, what is your carrying capacity? We know that carrying capacity is when dp dt equals 0, when we stop growing. And that's going to happen when p is 0 for this piece, and when p is 20. So we can calculate that limit without even solving the differential equation. I also can ask you, what is the population when the number of bears is growing most rapidly? And remember, that happens halfway to your carrying capacity. So that happens when you have 10 polar bears. That's when your population is growing the most rapidly. Again, these are two questions you can answer without even solving your differential equation. Your assignment for today is going to be your quiz review. You have a quiz on Tuesday. So we'll spend Monday tying up some loose ends and going over any questions you have. And then your quiz is on Tuesday. Again, please email me if you have any questions. I will post answers to the quiz review online so you can check as you go. I would spend some time on Sunday looking over the notes from Friday and today. And I look forward to seeing you on Monday.